Hello everyone who's watching this. My name is David Yasinski and I will explain how rocket engines work. First we're going to see how actually a rocket lifts off in a little video. There's a little thermochemistry involved. I won't talk to you about that, but you should know about negative 9.81, the acceleration of gravity on the rocket. You have to know that there's a lot of gravity pushing on a rocket, and the thrust needs to happen. It's pretty inspirational music, isn't it?
Sideways shaking.
That looks pretty cool, doesn't it?
Vibration was so intense you couldn't see the instrument panel. I thought we'd had it during the launch. I was hoping that Frank Borman didn't have his hand on the abort controller. He said he took his hand off and he'd rather die than make a false abort.
1 minute after liftoff, the Saturn V is already supersonic.
Well, the Saturn V is still the most powerful machine that man has ever devised. 20 tons of fuel a second, 7.5 million pounds of thrust. I think we were all surprised at how
It's a
strong
lot
that
of
thing
thrust,
was.
isn't it, for that rocket?
It had had 2 or 3 iffy missions before ours, but it was a piece of cake. It just worked beautifully. Unbelievable.
5 engines in the first stage blast the Saturn V to 7 times the speed of sound.
The second stage cut in. Big bang.
It's like Mach 4, Mach
At 40
5,
miles high,
isn't it?
it's still
When
accelerating.
you stage, you were thrown forward in the belts and then backward in the belts.
And I thought I was being catapulted through the instrument panel. All sources show that the stage is burning perfectly.
The third stage fires twice. First, the boost into orbit. The second burn takes the crew of Apollo 8 where no men have ever been.
Okay. Now let's go to the physics part of it. I'm going to explain a bit. So first we're going to talk about thrust. Thrust is the force that propels a rocket up. It's measured in pounds or newtons. This force is the result of pressure differences inside and outside the engine, and it's the gauge for rating the efficiency of a rocket propellant. All rocket engines produce thrust by accelerating gas. We can see this force using Newton's third law of motion, that for every action there is an equal and opposite reaction. When the gas is reacted in the combustion chamber, pressure builds up, but near the bottom of the nozzle it decreases because it is expanded by the hot gas, the exhaust gas that flows through the rocket nozzle and is accelerated to the rear of the rocket. This force by the gas at the bottom, it's not compensated by the outside pressure. So the force by the gas, so the rocket reacts with the high-speed gas by pushing against the gas outside and goes the rocket goes the opposite way the gas is going. There's also pressure pushing forward against the inside walls of the expansion nozzle as the gas exits from the resulting pressure between the pressure pushing upon the chamber and the atmosphere outside it, which is and this pressure pushes or thrusts the rocket upward. The equation that can be used to find this force is F equals Q V subscript E plus the PE and PA. The Q is the rate of the ejected mass flow. PA is the pressure of the surrounding atmosphere, while PE is the pressure of the exhaust gas, and VE is their ejection speed. Momentum is conserved in the CR. You should know that momentum is a particle's product times its velocity, and the forces acting on the particles are equal to its rate of change. If there are no external forces acting on the system, it's constant and momentum is conserved. In rocket science, when the rocket is drifting, here's an example. If it's drifting in free fall, and at some time the rocket ejects gas at a constant speed, which is relative to the speed of the momentum. This would have it being conserved because the rocket will go faster from the other time, from that time that it was doing it. Next, impulse. Impulse is also connected to the momentum of the rocket. When a force is applied to an object for some duration, the momentum will change because of this. In rocket science, when the rocket is launched, it is deterred from rising by gravity. The gravity does not let it go up. All the gas that is being projected from the nozzle is thrusting the rocket forward or up, decreasing the mass of the rocket as it goes, making it lighter so it would go faster. Because the rocket is being propelled upward at a constant rate, the momentum changes drastically, making it accelerate faster. Since the rocket is involved with many forces acting upon it by a system of the particles, each particle's momentum and impulse is needed to be considered. The equation that can be used is the first P plus the sum of the impulses will show the other impulse, the new impulse, where the initial momentum is added to the sum of all the impulses. The ratio of the thrust to the flow rate of the gas weight ejected is the specific impulse, ISP. When the burning of the propellant is constant, the specific impulse is the time where the rocket provides a thrust equal to the weight used. Okay, now let's go into the mechanics of this. What makes up a rocket? There's the nozzle. The rocket is made, so I'm going to tell you the three: nozzle, combustion chamber, and injector. First, I'm going to talk to you about the nozzle. The nozzle is made of a convergent and a divergent section. It uses thermal energy created in the combustion chamber. The gas particles are slow moving and they're under high pressure and temperature. Then it goes through the nozzle throat and into the nozzle exiting area, where it turns into a low pressure, low temperature, and a high velocity gas. Having the chamber made long or the exit great enough, the pressure inside would be equal to the pressure outside to have the maximum thrust available. So if you make it long enough or big enough, you would have equal pressures on both sides, so it will be more efficient. If the pressure inside is greater, it is underextended, and if the opposite, it's overextended. Okay, that's simple enough. Next is the combustion chamber. It is the part where this chamber surrounds the propellants to ensure mixing combustion. To know how much volume of the combustion chamber, the formula you see is VC equals QVTS, where VC is the chamber volume, Q is the propellant mass flow rate, V is the average specific volume, and TS, of course, is the state time. Something related to this is a characteristic length of the combustion chamber. It's named L star, with the L star, of course, and this is more effective in calibrating efficiency. It is equal to the chamber divided by the nozzle sonic throat area. The combustion process involves a substance being oxidized, and advantageous to operate a rocket engine at a mixture ratio that is enriched in fuel. The mixture ratio is defined as the mass flow of oxidizer divided by the mass flow of fuel. Okay? The next part is the injector. It injects the propellant in the combustion chamber in the proper amounts and conditions to create an efficient combustion. What I want to tell you about are The propellants. There are three types. And these propellants are a chemical mixture burned to produce thrust in rockets and consists of a fuel and an oxidizer. There are three types of propellants: liquids, solids, and hybrids. Well, solids, hypergoals, and hybrids. Same things. In a liquid propellant rocket, the fuel and oxidizer are in separate tanks, and when released, they go through a series of pipes and other things into the combustion chamber and can be moderated or turned off. These liquid propellants can be classified into three types: petroleum cryogens, which are liquefied gases, and hypergoals, which are propellants that ignite spontaneously on contact with each other and require no ignition, each with advantages and disadvantages. Solids come in homogeneous and composite families. The propellant motor consists of a casing with the propellant inside, combusting and producing hot gas, and the combustion cannot turn off. That's a disadvantage. Hybrids have the fuel as a solid, while the oxidizer is the liquid. These can be moderated and have high efficiency, but difficult for large thrusts. Also, it has the structural task of closing the top of the combustion chamber against the high pressures and temperature that the chamber has. So it's like a very big carburetor for a car. Also, it is a very big component with the greatest impact on the efficiency of the combustion. An important part in the design is to have the combustion stability. It needs to stabilize combustion, because the propellant, when it combusts, it creates shock waves, heat, fluxes, and vibrations that can be very destructive to the engine. Lastly, you need to keep the engine cool so it doesn't blow up, which is not very good for the astronauts and everyone around. So, heat is transferred from the high temperature of the gas to the combustion of propellant that requires attention. To meet this challenge, there are several chamber cooling techniques that have been used. Regenerative cooling is the most widely used method of cooling a thrust chamber. It is accomplished by flowing high velocity coolant over the backside of the chamber wall to cool the hot gas liner using convection. The coolant with the heat input from cooling, so the cooling with the heat input that took the heat in from cooling the liner, is then shot into the injector and is used as a propellant in the combustion chamber. So it's not thrown overboard, but actually used to put more thrust. Some designs were created, such as tubular walls and channel walls where the coolant flowed through. So there's different techniques for regenerative cooling. Also, there's dump cooling. It's the same application like the regenerative cooling, but instead of put into injector, it's dumped out in the back of the nozzle. So, bye-bye. Lastly, not really lastly, there's like a couple more that are used, but they're not really that important. Film cooling provides protection from the heat with a thin film of coolant in areas of high heat influx. So the parts where it's very high in heat, such around the combustion chambers in alleyways, dark alleyways, and there's also some more that are widely used that I'm not going to talk to you about because they're very minor. So that's it mostly about it, how rockets work. There's thrust, impulse, momentum, some physics involved. The mechanics of it, how it's made, is the nozzle, combustion chamber, and injector. Thank you for watching. Goodbye.